Hi everyone, my name is Walerian Sobczak. I'm a software engineer in a company called Zendesk. And today I'd like to talk about processing streams. So in software engineering, we mostly build systems and applications which could be based on either heavy computations, where CPU cycles are the bottleneck, or based on data. So the data is the primary challenge. The quantity of data, the complexity of data, or speed in which it is changing. Most of the applications today are data-centric instead of compute-centric. And raw CPU power is rarely a limiting factor for systems we build. Data is usually the biggest problem, and we need to store data so we can find it later. We need to remember results of expensive operations to speed up reads. We need to enable search and filtering the data. We need to analyze large amount of accumulated data, and we need to send some data to another process so it can be handled asynchronously. And for all these different tasks, we would probably use different tools. So for storing data, we would use a simple database. To memorize some operations, we can use a cache for searching and filtering some search indexes. And for analysis, we can use batch processing. And to asynchronously process data, we would use streams. Martin Kleppmann, a researcher in distributed systems, came up with the following classifications. So there are 3 different types of data-dependent systems. First of all, there are services, so-called online systems. So we ask for something or send an instruction, and sometime later, the system hopefully gives us an answer. So databases, caches, search indexes, web servers, and many other systems work like this. Response time is usually the most important measure here. And also availability is often important. So if the client can't reach the service, the user will probably get an error message. Secondly, we have batch processing systems, also known as offline systems. Such system takes a large amount of data, runs a job to process it, and produces some output. Jobs often take a while, from a few minutes to several days. So in most cases, there is no user ending for the job to finish. And batch jobs are often scheduled to run periodically. For example, once a day, once an hour. And the primary performance measure of batch jobs is throughput. So the time it takes to crunch through some data set of a certain size. And finally, we have stream processing systems. So these are somewhere between the online and offline processing systems. That's why it's sometimes called near real-time processing. Such system, rather than responding to requests, it consumes inputs and produces outputs. So it's kind of similar to batch processing. However, a stream job operates on events shortly after they happened. So batch jobs operates on a fixed set of input data, and we have like this continuous processing. The input here is unbounded. So we still have a job to do, but the input is never ending. It's like a stream of data. So there is always like more work to do. We never finish. So the difference between those batch processing systems and stream processing systems allows us to have lower latency. So in reality, a lot of data is unbounded because it arrives gradually over time. Our users produced data yesterday, today, and will continue to produce it tomorrow. Unless we go out of business, this process may never end. So data set is never complete in any meaningful day. Batch processors must artificially divide the input. So we divide this into some chunks. For example, we process an hour's worth of data at the end of every hour, or we process days worth of data at the end of every day. So the changes in the input might be reflected in the output a day later. Sometimes it might be too slow for us. We can run the processing more frequently to reduce this delay. Let's say we would like to batch process some data, maybe a second's worth of data at the end of every second. But then we could just do it continuously and abandon this fixed and artificial division. And that is the idea behind stream processing. So in general, stream refers to data that is incrementally made available over some time. That's basically the same concept as in Unix standard input and output, in maybe lazy lists in some programming languages, file system APIs, TCP connections, or just delivering audio and video over the internet, which is also called streaming. And in this talk, I want to discuss streams as a data management mechanism. So this unbounded and incrementally processed counterpart to batch data processing. So let's start with some basic terminology of streams. So we have an event, which is an equivalent of a database's record. It is a small, self-contained, and immutable object containing the details of something that happened at some point in time. An event usually includes the timestamp, which basically tells us where it happened, when it happened. And the thing that could happen might be really anything. So it can be an action that a user took, such as viewing a page, making a purchase. It might also come from a machine, such as some periodic measurement from some temperature device. Or it might also come from some other computer, which tells us what's the CPU utilization metric. So the event in streams is produced only once by a producer, also known as a publisher or a sender, and then potentially processed by multiple consumers, which are also known as subscribers or recipients. And events are usually grouped together into topics or streams. So a common approach of notifying consumers about new events is to use a message systems. So it's a system where producer sends a message to the consumer. And there are two most popular ways of doing so. The first one is a direct messaging. So we have a direct network communication between a producer and consumer, and there is no other component in between. They are suitable for some cases, but they require the application code to be aware of the potential message loss. So the producer must be ready for any outage with consumer and so on. So the second option, even more popular, are message brokers. So those are a kind of database that is optimized for handling message streams. And it runs as a server with producers and consumers as its clients that are connected to it. And producers write messages to the broker, and then broker sends them to consumers. In this way, they can more easily tolerate clients' failures, because client can come and go, and the question of durability is moved to the message broker. So examples of such systems are Kafka, RabbitMQ, or Amazon SQS. So I mentioned that events in streams are immutable objects. And we normally think of databases as storing the current state of application. So the representation is optimized for reads and is usually the most convenient for serving queries. The nature of state is that it changes. It always changes. So the database supports only not only reads, but also updates and inserts and deletions of data. So how does it fit with immutability? So whenever we have state that changes, that state is the result of the events that mutated it over time. For example, a list of currently available seats in a restaurant, it's a result of all reservations that we have processed. The current account balance is the result of the credits and debits on the account. And for example, let's say response time graph is like a representation of all individual requests that are aggregated and then calculated. No matter how the state changes, there was always a sequence of events that caused those changes. Even as things are done and undone, the fact remains true that those events occurred. The key idea is that mutable state and an append-only log of mutable events do not contradict each other. They are just two sides of the same coin. So the log of changes, also known as a change log, represents the evolution of state over time. So in mathematics, we could say that application state is what we get when we integrate an event stream over time. So if we change this changelog durably, that simply has the effect of making the state reproducible. And immutability in databases is really old idea. For example, accountants have been using immutability for centuries in financial bookkeeping. So when a transaction occurs, it is recorded in an append-only ledger, which is essentially a log of events describing money or other goods that have changed hands. And the accounts, such as profit and loss or the balance sheet, are derived from these transactions from the ledger by summing them up. So if a mistake is made, accountants don't erase them or change the incorrect transaction. Instead, they add another transaction that compensates for the mistake. For example, refunding an incorrect invoice. The incorrect transaction will live in this log forever because it might be important for some auditing reasons. And immutable events also may include some more information than just the current state. For example, if you have a shopping website, a customer may add an item to the cart and then remove it. So the second event cancels out the first one from the point of view of the order fulfillment. But it might be useful to know for analytics purposes that the customer was considering this item, and maybe he decided to buy something else, or he never come back to us. So this information is recorded in an event log, but it would be probably lost in a database that deletes items whenever customer removes them from the cart. So far, I talked about where streams come from and how they work. So what remains is to discuss what we can do with the streams once we have it, and we can process it. There are basically three options. The first one is to take the data in the events and write it to database, cache, search index, or any other storage system, from where it can be then queried by other clients. It can be a good way of synchronizing the changes in our system, especially if the stream consumer is the only client writing to the database. Another option is to push the events to users in some way, for example, by sending them an email alert or a push notification, or just by streaming the events to the real-time dashboard where they are visualized. And in this case, a human is the ultimate consumer of the stream. And finally, we can process one or more input streams to produce one or more output streams. Streams may go through a pipeline consisting of several such processing stages. And eventually, they end up as output in either option 1 or 2. So stream processing has long been used for monitoring purposes, where, for example, an organization wants to be alerted if a certain thing happened. We have fraud detection systems, which monitors some usage patterns of credit cards and block the card that looks like it might have been stolen. Some trading systems need to examine price changes in a financial market and then execute trades according to some specified rules. Additionally, there are some military and intelligence systems which need to track the activities of a potential aggressor and raise the alarm if there are any sign of an attack. Secondly, we have complex event processing. It's like a special approach for analyzing event streams, especially geared towards the kind of application that requires searching for certain event patterns. So it's similar to the way that regular expressions allows us to search for certain patterns of characters in a string. This complex event processing allows us to specify some rules to search for some patterns of events in a string. And such systems usually use some high-level language like SQL or even graphical user interface. And user can describe the patterns of the events that should be detected. And then when the match is found, the engine emits a complex event, hence the name, with details of the event pattern that was declared. And another area in which stream processing is used for is analytics of streams. It's more oriented toward aggregations and statistical metrics over a large number of events. For example, we can measure the rate of some type of event, so how often it occurs per time interval. We could calculate the rolling average of a value over some time period and compare current statistic to the previous time intervals. So, example, we can detect some trends or to alert on metrics that are unusually high or low compared to the same time, for example, last week or last month. So Apache Storm is a distributed stream processing computation framework which is written in Clojure. It integrates with any queuing system and any database system. A Storm application is designed as a topology in the shape of directed acyclic graph with spouts and bolts acting as the graph vertices. So edges of the graph are named streams, and they direct data from one node to another. The architecture of Apache Storm might be compared to a network of roads connecting a set of points. So traffic begins at a certain point, called a spout, and passes through other points, called bolts. And as I mentioned, some of them, there are only 3 basic abstractions in Storm: spouts, bolts, and topologies. So a spout is a source of the stream in our computation. Typically, a spout reads from some message broker, such as RabbitMQ or Kafka. But a spout can also generate its own stream or read the events from external API, for example, some Twitter streaming API, which tells us whenever someone posts a tweet. And Storm already has most of the implementations for existing messaging systems. We have bolts. So a bolt processes any number of input streams and produces any number of new output streams. So most of the logic of the computation goes into bolts. So we can have them have their like custom functions, some filtering. We can join streams. We can aggregate streams. We can talk to databases or to other services from those bolts. And a topology is a network of those spouts and bolts, with each edge in the network representing a bolt subscribing to the output spout or another bolt. So topologies are like a multi-stage stream computation, which, when deployed, can run indefinitely. Additionally, there are tuples, which are the main data structure in Storm. It is like the representation of event, so a list of values. Apache Storm topologies are parallel and can run across a cluster of machines. So different part of the topology can be scaled individually. We can even adjust the parallelism of running topologies on the fly. It's also fault tolerant. When workers die, Storm will automatically restart them. And when a node dies, the worker from this node will be restarted on another node. So these basic abstractions of Storm provide us at least once processing guarantee. So it's the same guarantee that we get from message brokers like Kafka. And the messages are only replayed when there are failures. So to take full advantage of Storm scalability and fault tolerance, any production-grade topology would be submitted to a cluster of machines, and stored distributions are installed on the leader node, which is called a nimbus, and follower nodes, which are called supervisors. So the leader node runs the Storm Nimbus process and the Storm UI. Storm UI is just a web interface used to manage the state of our cluster. The follower nodes run the Storm supervisors processes. Zookeeper process, which is on a separate node, is used for coordination among the leader node and the follower nodes. So it's like a cluster management node. So the Nimbus process finds available supervisors via Zookeeper. And then the supervisors daemon can register themselves to the leader node. So our topology is submitted to the Nimbus process on this leader node, and then distributed among the worker processes running on the follower nodes. And thanks to the zookeeper, it doesn't matter how many follower nodes we run initially, we can always seamlessly add more. Storm will automatically integrate new nodes into the cluster. And when we start a supervisor, it allocates a certain number of worker processes. We can configure them, and these can be then used by the submitted topology. So in this image, we have like 6 worker processes, but any of those follower nodes could have any number of processes. So we could have like 1 process here, 3 processes there, and 2 processes in the last one. It doesn't matter for Storm, as Zookeeper handles it for us. So a little bit about fault tolerance. First of all, what if a worker dies? So the supervisor process will have it restarted, and with the restarts repeated in some short period of time, the worker will be reassigned to another machine. If an entire follower node dies, then its share of the work will be given to another follower node. And if the Nimbus dies, so this like leader process, the workers will remain unaffected, but we lose the ability to reassign the workers to other follower nodes. And so, for example, when Nimbus dies and another follower machine dies, then those processes won't be reassigned. The Nimbus and supervisors are themselves stateless, but with Zookeeper, some state is stored so that things can begin exactly where they left off if a node crashes or a process dies unexpectedly. Nimbus, supervisors, and Zookeeper processes are all fail fast, which means that they themselves are not very fault tolerant. Whenever a new unexpected error occurs, they shut down, and that's why we have this supervision that monitors them constantly and restarts them automatically if they ever crash. So in most Storm clusters, the Nimbus itself is never deployed on a single machine. We usually deploy it on a couple of machines. The same applies to Zookeeper, just to be ready for a single machine outage. Another thing to talk through is what happens is a bolt fails to process a tuple. So Storm provides a mechanism in which the source spout can replay a failed tuple. Spouts send out tuples to bolts, which emits another tuples. So in result, we have like entire tree of tuples. And if any child tuple of this original one fails, then any rollback step might have been performed on multiple bolts. And this sounds and is really complicated thing to do. That's why Storm allows the original tuple to be emitted again right from the source, so from the original spout. In consequence, any operations performed by our bolts must be idempotent. Otherwise, we can process some events multiple times, which is not something we would like to do. Tuple is considered fully processed when every tuple in the tree has been processed. So every tuple has to be explicitly acknowledged by all the bolts in the tree. So something about Storm in Ruby. Currently, there are 2 popular gems available. One is official and another is more community-driven. My examples are based on the latter one because, in my opinions, it has better abstractions of Storm components. And let's start with a simple spout, which is a source of our stream. This one auto-generates our stream, so it constantly generates a random number from a range of 1 to 10. Then we have a bolt, which count the occurrences of each randomly generated digit. And finally, here is a definition of a topology. So it's really simple topology. It has only one spout and one bolt, which reads from the spout. Basically, there are like those three classes combined. That's all we need for a simple topology to work. And in most cases, the topologies are a little bit more complicated. And I would like to share a couple of examples with you. So I work in a company called Zendesk, and I built a product called Cell. It's a Salesforce automation software. And our mission is to enhance productivity, processes, and visibility of sales team around the world. And those will be the real-life examples from our product. So first of all, we track interactions of our users with our systems for some analytical purposes. And we store every operation our customers perform. For example, creating, updating, and deleting objects, all their actions in our client's app, so web applications in browser and mobile apps on iOS and Android. However, in order to measure our users' engagement, we don't need to be so accurate. First of all, we are satisfied with some aggregates of these interactions, and we can just sum them every couple of dozen seconds, and we don't need to save every interaction in our database. Another thing is filtering. So we don't always need every interaction. We can filter out those that are uninteresting for us or just are unnecessary. For example, we may want to track only clicks on the front-end app. And finally, what we have, when we have these aggregates, we can do whatever we want with them. So here is like a simple graph of how this topology works. On the left side, we have this mobile and web apps, which emits those interactions. So every action of our user is saved and pushed to a Kafka cluster. From Kafka, we have 3 Kafka spouts, one for each platform, so Android, iOS, and web. And then we have one bolt which filters those mobile interaction, and another one which filters web interactions. And finally, we combine them all in a counter bolt, which just counts them. And when it's time to persist them, it pushes those aggregated interactions to the database. So here is how the code of the topology looks like. So the first 3 lines are just the Kafka spouts. This is something that the Redstorm gives us for free. So we just give it a name of topics from Kafka cluster, and we push them to bolts which are specified as the second argument. Then we have this mobile interaction filter bolt, which takes both Android and iOS interactions. This shuffle, as in the second argument of the source method, means that we don't care which interactions goes to which node. So they might be shuffled, and it might happen completely at random. And this is exactly the same thing for web interactions, but this time our source is interactions web spout. And in the end, we have this activity counter, which aggregates both web and mobile interactions. And this time we have, instead of shuffle, we have fields user ID. This means that all tuples with the same user ID should go to the same node. And here is how example bolt might look like. So this is the mobile interactions filter. First of all, we in this handle method, we sanitize the tuple. We filter out all interactions that are not UI based. So we want to have only those actions that were within the user interface of our mobile apps. Then we normalize the timestamp, we assign the fact type, and in the end we emit the data, the new tuple to another bolt. Similar thing for web interactions. This time we are not interested in any other interactions besides click. So we take only click ones, normalize the timestamp, assign the fact type, and emit the tuple to the next bolt. And this next bolt is the activity counter. So we can initialize some objects which are shared across this node. So here we have this hash of counts for each platform, and finally for the sum, so total activities count. And in the handle method, we, as usual, sanitize the tuple, increment the counts, and if it's time to persist, we store the counts in our database. This is some statistics from the last 3 months on the production environment. So such topology can handle, on average, over 100K requests per minute, and the transaction time is really low. It's under 1 millisecond. Another example would be email intelligence. Let's imagine a following scenario. So our sales team receives a lot of emails. The fact is that not all of them are actionable, and which makes them less eager to handle them immediately. However, we may receive an email which has information related to some important deal, which currently needs to be read and processed, and may be replied to. So we created a machine learning model that can automatically score each email and decide whether its sentiment is negative or not in the context of a deal, and accordingly notify the owner of the deal. Thanks to this feature, we can be notified whenever the model decides that a deal might be at risk, and because of an email we've just received. So this pipeline is really simple. Whenever an email is sent, we publish an event to Kafka cluster. Then we have this Kafka spout, which pushes the tuples to extraction and filter bolt. So we want to filter only emails associated with some deals. And then we have this reply parser bolt, which takes only the last part of the email chain. So we usually have long email threads, and we are interested only in the last message. And we have also a machine learning model for this one. And finally, we have this scoring bolt, which applies the machine learning scoring model and calculates the email sentiment. So it says, it tells us if whether the email has negative sentiment or not. And finally, we save the score by issuing an HTTP call to our backend service. So I'd like to briefly talk about costs of such undertakings. I think it's sometimes something that is often unmentioned in technical talks. So here's a standard pricing for AWS machines, which we use in company for Storm topologies. Our product is backed with 25 topologies. Each can handle around 100K requests per minute. We found out that a suitable configuration for this amount of topologies would be a cluster of 2 leader nodes, 2 zookeeper nodes, and 4 follower nodes, which sums up to less than $1,000 monthly. And finally, I would like to talk about some alternatives to Storm. Because Storm is not the only player in the world of stream processing, we have also Apache Flink, which implements fault tolerance with a combination of some checkpoints and replays, and they claim that they support exactly once message processing. We have also Apache Samza, which is used extensively by LinkedIn, and we have Confluent KSQL, which is a streaming engine that enables real-time data processing against Apache Kafka. And we have also some cloud-based services such as Kinesis from AWS, Dataflow from Google Cloud, and Stream Analytics from Microsoft Azure. And that's all from me. Thank you very much.
Yes, thank you. We have not so much time, so if you have some questions, please ask on the break or on the lunchtime. Yeah, maybe one question. Yeah.
Thanks for the talk. My question is why did you decide to put up your own cluster of Storm rather than using a cloud solution like Kinesis or Dataflow?
Okay, so when we started this, there was no cloud-based solutions. So we had to come up with some more customizable ones.
If you had to do this now, would you still do it the same way, or maybe use a cloud solution?
I think that personally, I would try this AWS Kinesis. It looks really promising, and I tried it for some more toy applications, and yeah, I think that would be my choice right now, just to give it a try.
Okay, thank you.
Thank you. I think that's all. Thank you.
Thank you.